好，张伟腾 ，try to write down. Use this equation. Okay, you come here to write down EY equals to from the first equation. Okay, it's okay, easy, right? From this one, try to write down EY equals to. Okay. Right. And I need another student to help me with Li Guanyi. Okay. Try to use this equation to write down EY equals to. And who is next? Zhong Pingjun. Okay, come here to ready. I want you make an equation from E and E. To write down an equation because EY equals to something and the EY equals to something. They are the same, right? So write down. Okay. So what you obtain from this equation and you done? For sure. And then this equation is right down. So something equals to something. They are both of them are EY, right? Make sure you didn't make a mistake. So for this equation,
Professor, I don't think that is correct.
Make mistake, right?
I think so.
Okay, come to help this. Maybe make mistake. EY equals to Zhang Weiteng, come on. That's basic math. Maybe you can wait up this answer. Minus J EY equals, maybe we should slow down, right? J U beta. Yeah, I think you have the positive negative overlap. Minus. Is correct. Okay, your answer is correct. But this is wrong, right? Okay. Okay, I think this one is correct. How about this answer? So your answer EY equals to J omega answer minus. Okay. Okay, so. Okay, right now, and give us the final answer. So Hx equals to, you do some organization. And what Hx equals to? Okay, we are almost there. We are almost there. This is one of the important checkpoints about mode. Everyone try to do that. I think you can do that. Be careful. You need more steps. More steps. Try to organize, clarify, try to move all the elements to one side. Do that step by step, carefully, to obtain the result. Everyone try to do that. And you will understand. Why are there so many equal marks? Try to have Hx. Everyone. I'm sure this is correct, and that is also correct for 2 Ey's. So there are 2 equations. Can you do that? No? Is this a college level math or not? This is high school level math. Come on. You can do that? You don't want to do that? If you don't want to do that, you can go. What is J multiply J? J equals to 对啊。这样的也是啊，这种基本的运算，不知道为什么会算错，试试看。Anyone show me the answer if you got one. 5hx from these two equations. If you finish, let me know. We have this equation and the orange equation. You finish.
我帮我们，你那个再要补掉。
他再画一下，把它弄更简单，更小。没错。close， 在很接近，我要 hx。 Okay, thank you. Difficult, huh? Okay, try to see my derivation here. I post on website as well. This one, okay, follow my answer. It's just write down carefully. This one equals to this equation. No problem, right? This is where we start. Equation 1 equals to equation 4. For E, we try to find out what is EY, okay? And you will have this equation. So first you need to list this one correct. After all, you try to organize, you put HX together this part and this part for the left side in Hx. Okay? Then you will have this. Okay? And also you put others like partial differential Hz partial to respect to x and Ez differential to y. You put the rest of side to here, the rest of part. And for Hx, this parameter you can change this one in this form. Beta omega epsilon, we have the same denominator. Then you will change this omega mu multiply omega epsilon, and you have this term. And for this term, you miss the beta, right? So multiply beta and you obtain this term. This is the most important part. For the denominator, you have omega epsilon b. Then the others will be easy. You just change, divided by, and you have. Okay, let's find out the final result. You will obtain Hx equals to, you put upside down and then you multiply this one inside, right? You are equals to omega square mu epsilon minus beta square and multiply omega epsilon beta. It's minus j omega epsilon multiply omega epsilon beta, which is minus j beta for the first term. Okay, is minus j beta and Hz divided by the partial differential with respect to x, and plus is j beta and multiply omega epsilon beta. You cancel beta and the beta is, so you left j. You left only j omega epsilon. J omega epsilon. Multiply the rest of term E z partial y. Check the answer. Omega epsilon. Okay. Then you can take a j outside because they are all the same. Y minus beta. Okay? So this is the final answer. Okay, this is the correct one. This is the most important term we try to derive. This is where the mode come from. This is the mode, where the mode come from. Try to remember this one. If you are talking about mode, maybe you will see this again and again. Okay, and this is only for Hx. We have also Ex and Ey and Hx and Hy. Because we have 6 equations, right? Let's try to review what did we do. Try to review. Okay, what did we do here for? How do you obtain this one? How? Okay, first we try to write down the general form of E field and H field, and we try to simplify this form by using, we know this wave, this E field and the H field, it is propagating in positive Z direction and in a lossless media. So you can write down them like this one. Then you can use the partial, when you take the partial differential respect to Z, you can directly use minus J beta. Understand that? You can use minus J beta for your curl, the matrix partial to the partial Z. You don't use this, you use minus J beta because of they are both in these two forms. Okay, like your question asked me. This is the key. Okay, then you use Maxwell equation, the first equation and second equation. You put everything inside. You didn't do very difficult things. You do complex things. You separate the result for X component, Y component, and Z component. Then you obtain 6 equations because you have Maxwell equation, the first equation, the second equation. For each equation, you obtain X and Y and Z. You obtain 3 components for first equation and 3 components for second equation. So you find 6 equations. From these 6 equations, you can make an equation to eliminate, like for Y or other things. Okay. Now you can understand my. Okay. After all, you can understand my PowerPoint. Okay. Let me use my PowerPoint. I think all of you cannot follow if you just read my PowerPoint. But now you can, most of you can read because you follow. You try to derive, then now you can understand my PowerPoint. Okay, a lot of math, but not difficult, just very noisy, annoying. It's very annoying. Too many maths, right? And divide, and then you use a lot of try to organize, just time wasting. But now you know the reason. Okay, so we start from the equation of E and H as the black color. What I wrote down. Okay, this is where we start. We need to understand what is the wave propagating in Z direction in a lossless media. So you write down these two formation of E and H. Then you try to use Maxwell equations using source-free case. You don't have the source. You don't have M and the J. You have only the sourceless equations. Okay. From these two equations, this is what we did on your whiteboard. You put everything inside and write down everything, and you obtain 3 equations. And you change your partial differential respect to z to minus j beta. And because this is minus and minus, you obtain positive. So you obtain 3 equations from the first Maxwell's equations. Okay? You separate x and y and the z. They are all independent to each other. You obtain 3 equations. Okay. From these 3 equations, you organize to obtain what is y, ey. And also, you will obtain another 3 equations from the second Maxwell equations. So there are 6 equations, and you can make, you pick the first and the number 5 equations. You make an equation to delete ey. Okay? Delete ey, then you can obtain hx, well, xy I write down here. Okay? So you have the same result from here. Okay? It's a long derivation. I know. You should do that, and you will know more. Okay? You will find there is a very special denominator we call omega squared times mu epsilon minus beta squared. This part, it was the k squared before, right? Remember, when we used the wave equation in chapter 1, we said this is k squared. We told you in TEM mode, k is beta. Now, k and the beta, they are different. K is here, beta is here. They are different things here now. All of you should have very good memory. When you are in chapter 1, when we are doing a midterm exam, k equals to omega squared multiplied mu epsilon. Let me try to remind you, because your eyes show me you forgot. When you, in chapter 1, we try to derive the wave equations. Remember, this is our older PowerPoint. Chapter 1. We try to derive wave equations. You take a curl again to the first equation. You take a curl again for a second equation. You find out the result. You try to find what does E field looks like. You try to solve a second order PDE to obtain your equation E for your E field. Remember, this is chapter 1, wave equation. When you do that, this term, we say this is k squared. Omega squared multiplied mu epsilon. I told you this is k squared. Remember? This is k squared. And in this case, k is the propagation constant. It is the phase constant. It is wave number. It is 2 pi over lambda. Wave number, how many waves in 2 pi? We told you that, right? Remember, when you do that, we say k is beta. This is how it propagates. But now k is not beta anymore. K and the beta, they are different things. The things goes more complicated. Why? because this is only a special case, this is a TEM mode. This in chapter 1 is very simple. In chapter 3, I'm telling you that there are more difficult mode other than TEM mode. This is a special case. This is the easiest case because beta is K. But here in chapter 3, they are different. Your H field in X direction, it is something relevant to EZ and HZ, which never existed before. You remember? When you are in chapter 1, I told you this is 0. Remember? I told you we don't consider that. We know the plane wave S cross Y equals to Z equals to the conjugate of H. It is the pointing vector. Right? Use your right hand and you know E cross H and the direction of P, right? But now it's not true. Because we have this term, EZ. EZ is the same as your direction of propagating. Why? This is more general. This is the more difficult part about in chapter 3. When we talk about waveguide, that happened. When you talk about coaxial cable, that haven't happened. This is a plane wave. So easy case. But in chapter 3, waveguide, this one show up. Okay? Because of the equation of our general equations about all the, if you consider X, Y, Z for your E and the H field, this is a very, very difficult concept. Okay? Okay, when you solve that this one, you find out, oh, K, blue one is K, this is beta. Why? Well, it's common. You're confused about K and the beta. Well, they're the same? Yeah, not the same here. Because you consider something different. Okay, let me read a sentence. Phase constant and the wave number are often treated as the same thing. Phase constant, this one is beta, and this is K. Beta and the K, they are the same, always, often the same. What does that mean, often? When in TEM mode, they are the same. But not TEM mode, they are not the same. Okay? So, instead, for TEM transmission line, coaxial strip line, they are constant, they are equal. Okay? TEM, they are equal. Waveguide is one case where you need to understand the difference between beta and the K. If you want to understand waveguide, the first thing you need to understand is K is not beta. Okay? Okay, I write down, you can translate if you need. Okay, let's do some organization now. So, for the TEM mode, beta is K. So, your beta is K0 multiply epsilon R. We did this last week, remember? If you don't remember, go to watch a video for last week. If it is TEM mode, beta is K0 multiply epsilon, the square root of epsilon R. What is K0? K is omega square root mu epsilon, and K0 is omega multiply mu 0, epsilon 0. K0 is the K in the air. We also mentioned that last week. If you don't have any clue about what I'm talking about, go to watch the video last week. And last week, we focused on the quasi-TEM mode. We focused on the microstrip line, right? I try to introduce microstrip line where beta equals to K0 multiplied the square root of epsilon. E, it is a numerical epsilon. It is a numerical result. And then you have another equation, remember? For the quasi-TEM mode. Okay. For waveguide, it is important to introduce you that beta equals to the square root of K0 squared minus Kc squared. Where does that come from? It comes from the equation. I'm telling you that the red box is Kc squared. The total denominator is Kc squared. It means it is the cutoff wave number. Cutoff means a boundary. A boundary. What happened? I think all of you know the cutoff, right? Cutoff frequency, right? At the boundary of frequency, and this is the boundary of the wave number. The total is Kc, and the blue one is K squared. So then you will have an equation. What is beta? Beta is the square root of K0 squared minus Kc squared. Okay? If the material is air, you use K0 for the air, and the Kc is the overall denominator. Okay? Okay? For this one is new. For waveguide, and then you got a beta. You obtain the beta from what we derive here. This is from the denominator. I will give you a little time to understand and raise your hand if you don't understand. It is common you don't understand. It is uncommon you understand. So don't worry about that. If you don't understand this part, show me your hand. If you all of you understand this thing, it's no problem. I can just continue. Anyone have a problem about what is beta? For 3 different transmission lines, 3 different modes, 3 different equations for beta. Last week we know these 2, right? This week we have one more for the beta. Understand? Okay? Don't be scared. Well, if you don't understand, just let me know. Okay. Okay, so everyone understand. The beta for waveguide, maybe your question is what is Kc, right?
Yeah.
We will try to derive. But K0 is easy. K0 is this one, right? You will have material. And now it's Kc. You will know Kc after. Okay? Kc is only the thing I haven't told you yet. But try to think like, oh, there is a boundary here. And it is relevant to the equation we derived for this equation. All the denominator is Kc squared. Okay. Okay. Let's try to talk about Kc. Okay. Let me continue something after you know the beta. after you know the beta, we know the phase velocity Vp equals to omega over beta, right? All of you know this equation. So for the TEM mode, Vp equals to omega over k. And for the quasi-TEM mode we introduced last time, it is omega over beta as well. But your beta, now it is something relevant to square root of epsilon E. So you change this one. Okay, check the video for next week if you have a question about the Vp for the quasi-TEM mode for your microstrip line, the Vp. And for this one, it is also equal to omega over beta, and your beta equals to this. So this is your Vp for waveguide, for your the waveguide with the material is air. Okay, just put the same equation. You put different beta for Vp. It's not so difficult. And for the lambda wavelength, guided wavelength, we call it lambda G. G means guided. Okay. So for the TEM mode, lambda G equals to 2 pi beta. Beta is k, and we can transfer the k is k0 multiplied square root of epsilon r. So it is the lambda 0 over epsilon r. What is lambda 0? Lambda 0, it is 2 pi over k0. In the air, it's lambda in the air, so it is c, speed of light, divided by f. Okay? So this is lambda 0. So lambda g is lambda 0 divided by the square root of epsilon r, what we learned in chapter 1. And for the quasi-TEM mode, the microstrip line is lambda 0 divided by epsilon e, square root of epsilon e. Okay, you can tell the difference because this is quasi-TEM mode. Okay, what we did before. But in this term, in waveguide, it is 2 pi over beta. So you put the beta in again. So you can try to simplify the equation. You just use different beta for the same equations. You can obtain Vp and lambda g. All of them have the same equation except beta, right? So once you know the different beta, you will use the same equation to obtain different lambda g, different Vp. Okay. And let's take a little break and let me finish